better outcomes, better drilling outcomes, better production outcomes, better yield. These are all things that we heard in the last 6 weeks through the Rose Rock Bridge program. Yesterday, we had the opportunity to visit H&P and go see the amazing control system that has been built there. Better drilling outcomes. It's written on the wall, but there's a lot of details underneath it that's all required to make that work. I'm Nathaniel Hartwig, founder and CEO of BiaTech, joined by Rick Gillis, our head of process technologies. Every industrial system has operators, humans at the switches, pushing buttons, turning wheels. Every one of them has dashboards, but none of them have AI engineers in the field. So, as we mentioned in the last 6 weeks, we've been reading 10Ks. We've been listening to comments that you've made. We've asked questions. And we've discovered that better outcomes is the theme amongst all of the different people producing things. Whether or not you're looking for more flow, whether you're looking for safer operations that you have, whether or not you're drilling wells better. When we're talking about physics-informed machine learning and empowering operations to make better decisions, what we're really talking about is replacing the dashboard with physics-informed models that can become the AI layer that sits across all industrial applications. So we also visited University of Tulsa, and as we were kind of walking through University of Tulsa, a great application laboratory for flow testing. And as I was walking around, we were talking with Tim, one of the entrepreneurs in residence. And one thing that we talked about was when you're designing a system, the factors of engineering safety that go into that system's designed for all of the various applications that may actually happen or all of the various conditions that may be set. Pressure, temperature, flow, different yields, different products. It's designed in such a way that it can handle all of these items, but there's only one way to run that best in that moment. And that environment, with those conditions, with those inputs, with those desired outputs, there's only one way to run it best. And only physics can tell you what that way is, that best way, not a historical dashboard. I'll make this as an example for you. If you're driving a car and you're driving 30 miles an hour, only physics can tell you exactly where you will be in 10 seconds. Whether the inclination of the steering wheel is a certain way, whether a light may or may not turn yellow and green if you're at a red, only physics can tell you exactly what that will be, not a dashboard. So that's what we provide, is physics-informed neural networks, physics-informed machine learning that resides in these NVIDIA supercomputers that sit at the edge and engage with the human that's answering questions and that's making physics-based recommendations in real time. So that is our platform. Our platform, this AI layer that sits across industrial applications, observes, reasons, and advises all at the edge. It understands equipment behavior, and what we do is run physics-informed machine learning models that can run tens of thousands of times faster than computational fluid dynamics models. So I'll say that again. When you're running a physics-informed machine learning model, you're running tens of thousands of times faster than a traditional computational fluid dynamic model, which means that you can solve higher parameter models in real time at the edge. So you can give somebody an answer that they would never have access to before. So we have one platform. We're pilot ready today. Whether or not you're looking to have more intelligence for flow, more intelligence in drilling operations, more intelligence in field operations, this is a real enclosure. These are real models. That's a real rover. It was actually running in a pipe yard last Monday, counting pipe. So there's real applications of edge intelligence based today. When AI engineers and GPUs are deployed, we can empower humans to make better decisions. Do you know who the best driller in the world is? It's the one sitting in the drilling rig. Otherwise, they wouldn't be sitting there. So how do you take that human and give them more intelligence to make better decisions in real time? That's what we're trying to do. Your workers are the best at what they do. we can help you make them better. What we're asking for, 6 weeks, one workflow, one SME, one metric. In 6 weeks, we can prove to you physics-informed machine learning can help your operations be better. Give us another 6 weeks past that, we'll put it into the field and help you prove that in real life. This is the team. Our team has deployed over 22 systems. We have revenue already. I started as a field engineer for Mobil Oil and ran a $1.5 billion division for equipment at SLB. Rick was leading process flow technologies, creating much of the flow separation technology that exists on rigs today. Mario was a founding member that was a postdoc that was credited as part of that team for inventing physics-informed machine learning models. Sam, our lead developer, was brought to NVIDIA GTC 3 years ago and was the first one to launch a physics-based model inside of NVIDIA Omniverse, the first one presented at the conference for that. We have the right team, we're execution-oriented, and we're ready to work with you on the challenges that you have. National Lab of the Rockies. So today we have 4 grant applications. The National Lab of the Rockies has asked BiaTech to be their physics-informed machine learning provider to help them with their grants, $10 million grant opportunity. If those are awarded, BiaTech will receive over $700,000 from those grants. I'll go a little bit faster. Tulsa can be our home. This isn't a push, it isn't a pull. This is a natural evolution of a model where your client base is supported locally. Special thank you to everyone at Rose Rock. We're happy to be here, and we just really appreciate the opportunity. Thank you very much.
Great job, Nathan. All right, we'll do our 4 minutes of Q&A.
Job. Silly question. How much historical data is required before the value starts to show up?
What's amazing is that you can actually create synthetic data until you have real data. So we estimate about 10% of the total traditional data that you'd need with pattern recognition systems like machine learning, which has been around since the 90s, right? Yeah. So about 10% of the data is required because we can actually create synthetic data using physics models. Yeah. Thanks.
Could you elaborate on the 22 devices that you've deployed today? What kind of use cases and scenarios are?
So we started with one wedge on drill pipe. And so these are all focused on drill pipe integrity. And from that, we'll then move into flow this summer, and then the visual management of the same systems using the rover technology. Three minutes for questions.
In the physics-informed neural net approach, you're training it on like full physics simulations. What's the computational resource behind getting that level of like physics, like to base neural net shortcuts off of? And how does that process work with BiaTech to build out those kind of models for whatever use case you're trying to get to?
Yeah, it's a great question. So the computational horsepower is required up front in making the first pin or the first PIML. Once it's moved to the edge, it runs here. Yeah, so this is the kind of less than 7 seconds, which used to take days or weeks to run in prior models, but it's all running right here. Yeah. Thanks.
Is each solution made specifically for the one customer? Can they be moved over to somebody similar, like if it works for Devon, would it work for BP or Shell, or is it specific to Devon's needs and you'd have to go and do the same process? 6-month trial or 6-week trial with any other customer?
Great question. The answer is it generalizes. And so when we're training learning models, we deploy an initial model that was based on surrogates, based on physics that was then created for that application. But physics is transferable. Gravity is transferable. Flow is transferable. So multi-phase flow through thermodynamic systems, steam, water, non-energy contributing particles flowing 30 miles an hour through a pipe is the same flow dynamics as you would have in oil and gas coming up through a well. And so the models do generalize across different conditions.
What's the base physics model that you use? Is it something you guys developed or is it something you partnered on?
We've made 100% of everything we've developed ourselves. Yeah, so we started with a bunch of PhDs that we locked in a room and said, what's the physics equation for each of these options? We then built a geometry library associated with it. Top drive, mud pump, drawwork, each of them have specific geometries. Natural gas compression station, distribution stations, they'll have specific geometries. And then from that, physics models plus geometries, we then loaded it with live data to see if it can detect anomalies within it.
I see a great deal of technical expertise on your advisory board, which is great. Can you tell me more about who and how you will expand in your market?
Yeah, so we're not intending to be SLB, 100,000 employees. We're going to work with channel partners to distribute things that are people intensive but still need people facing it. So our go-to-market path is to enable small to medium-sized businesses to continue to deploy our technology in people-heavy tasks. Example would be drill pipe inspection, where they would use our technology and then they would still be the service company to go do all of those tasks. So that's how the channel is in there. And then working directly with large companies to then solve specific problems. If that's a platform as a service, we'll do that, but otherwise we'll partner with others to bring this to market.